which up to this point, we've dealt with functions in our differential equations that are continuous. Things like polynomials, things like exponentials, things like, I don't know, what else? Sines and cosines, right? Completely continuous. But we haven't dealt with situations where there's discontinuity. What would it mean to have a forcing function that pushes and then stops, goes away, and then pushes and then stops and goes away? What would it mean to have a forcing function that pushes at a constant force and then immediately changes and pulls at a constant force? It doesn't oscillate so much as just change direction instantaneously. In the real world, something like that can happen, but we don't have a good method for modeling that mathematically. So this section introduces some big ideas for being able to deal with discontinuous functions and why the Laplace transform is really, really handy for this. And so I want you to think of the discontinuous functions as poking oscillators. So just like that question on the exam where I said you have a little piston that just pokes the oscillator every once in a while. It doesn't push and then pull and then push. It just pokes it every once in a while. What would that mean? So up to this point, we might be tempted to think of Laplace transforms as like another method that always works and never runs into problems. But the Laplace method has some limitations. So the first limitation is that it only works for linear differential equations. And remember, linear differential equations means our dependent variables are only ever to the first power, and they're not inside things. So we can't have sine of y or y to the third power or something like that. So that's the first thing. The second thing is that the Laplace transform method replaces calculus with algebra, which on the surface seems great, and we're happy about that. But what does that mean for the amount of work and the amount of attention to detail and the amount of, as I like to say, bookkeeping that we have to do in order to solve these problems?
It increases.
Yeah. So one of the problems that you guys ran into in solving that problem number 4 is like, oh God, I have to manipulate it. So the Laplace transform is great for replacing calculus with algebra, but that makes things more tedious. And of course, more tedious means more attention to detail is required. And as many of you have discovered in your own lives, sometimes we get lazy and we want to not pay attention to detail, and that's problematic. So things like partial fractions, things like completing the square, completing the square. Right? Things that you learned maybe a long time ago and you kind of put on a shelf, like, I'm never going to need to know that. Well, if you're using the Laplace transform method, you do, because it's a lot of algebra. But there's one other way that the Laplace transform method is incredibly useful for us. It allows us to use discontinuous functions. And so we're going to introduce what's called the unit step function. And you probably have run into step functions before. It's called the unit step function. That's why the U stands there. But it's really known as the Heaviside function. The Heaviside function, it's named after a person named Heaviside. His name was Oliver Heaviside. He's probably the most important person who you've never heard of. I doubt any of you have ever heard of him. If you have, then maybe you just do light reading around information theory. Any of you having are in the calc-based physics where you're learning about Maxwell's equations? Kind of the famous Maxwell's equations with del cross B and stuff like that. Does that sound familiar?
Absolutely
It
not.
sounds familiar.
Sounds familiar. Well, if you've heard of Maxwell before, James Clerk Maxwell was a physicist, an English physicist in the 1800s, and he came up with this brilliant synthesis of electricity and magnetism. He's the guy who brought us electromagnetism. He came up with this system of like 20 equations that all related these important things. But it was Oliver Heaviside who came up with a way of writing these equations not as a physicist would, but as a mathematician would. And so he took these physics equations and he simplified them, turned them into mathematics using vector calculus, and he wrote them in a much simpler form, the form that everybody to this day knows. Well, everybody who's studied this stuff knows. So when you run into Maxwell's equations, they're super famous, but they're not actually the equations that Maxwell wrote. They're the equations that Heaviside wrote. He also invented a method for conveying information over telegraph wires, a system of rules to follow to be more efficient with information traveling over telegraph wires. The telegrapher's rules is what they're called. He also invented coaxial cable. So like the copper wire with shielding around it that sends information. Um, he's a pretty important dude. He lived until 1925 and kind of died in obscurity in England. But let's put it this way: AT&T sent a team of people over to Britain to investigate all the different ways that they could steal ideas from him and patent them themselves. But the people who went over there were so impressed with Heaviside and how much he contributed to the field, they basically refused to steal the ideas and they offered him large sums of money as basically payment for his ideas. They were so impressed, the company basically said, "You are amazing. We want to give you money for these ideas." And this is the heyday of people just stealing ideas left and right. Now, he refused the money, which is very strange. But in the process of all of this, he became a bit of a minor local celebrity in Devon, where he lived. One of the things that he's still known for is what we're studying right now, which is the unit step function, which is deceptively simple. It is basically saying anywhere that t is less than some specific value a, the function has a value of 0. And anywhere that t is greater than or equal to a, the function has a value of 1. That's it. It's just one step that happens. So this is what u sub 2 would look like. Everywhere all the way up to t equals 2, but not including t equals 2, it's at a height of 0, right? And then as soon as t equals 2, it pops up to a height right here of 1. That's all that it does. It's a unit, meaning 1 unit, step function. Now, you've run into step functions before, but you've never seen step functions written kind of in line. So we're able to take this thing that's in piecewise form and rewrite it as a single statement, a single term. And what this thing does is it's off until t equals 2. When it switches to being on. And of course, off in this case implies 0. It has a value of 0 when it's off, and it has a value of 1 when it's on. And that's all that the step function does. Now, it seems like it's so simple, it's so obvious, but usually in mathematics and science, when somebody comes up with something that is so simple and so obvious that everybody else goes, well, duh, those are the moments when somebody has kind of pinned down a big idea, right? Those are the moments when somebody came along and pointed out something or wrote something in a particular way that made perfect sense. So this step function, it's not terribly interesting, but we can get creative. You can think of the step function like it's a switch. You can turn it off, it starts off, and then it turns on at a certain point of time. So this step function, the unit step function u sub c, is a switch that goes from off to on. So what if we wanted to turn on and off, but take on a different value? What if I wanted to make the step not just be 1 unit up? What if I wanted to make it 2 units up? What could I do to my unit step function?
Add a multiple?
Yeah, you just say, hey, what if I multiplied my unit step function by 2? Stick 2 in front of it. That means it would be off, and off is off. 0 times 2 is 0. But as soon as it turns on, the unit step function part goes up to 1, but then I'm multiplying it by 2. So now I can go from 0 to 2. And it happens instantaneously. This is a discontinuity. So this is unlike other functions that we've run into. It's a step function. So one way we can think of it is to imagine kind of turning the switch at a particular point in time. So if you were to do something like this, 3 u sub 1 of t, this would be a function that is 0 everywhere that t is less than 1, but then it jumps up to 3 everywhere that t is greater than or equal to 1. So just by throwing a number in front of it, we could make it jump up. If we can throw a constant in front of it and make it jump up to a constant value, what else could we throw in front of it?
Function.
Hey, we could stick anything in front of it, multiply it by this unit step function, and basically have a way to say nothing, 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 sine curve after this point in time. So we can turn on a function and turn off a function just by using multiples of this unit step function. And that's what we're going to see on the next page. So the Heaviside function only takes values from 0 to 1, but we can use function transformation rules. Remember those rules from pre-calc where it's f of x minus 3 that shifts the function over 3 units to the right, or f of x minus, or f of x plus 2 that shifts it 2 units to the left. Do you remember those days? Yeah, this is what you were learning it for, is we want to be able to think of anything times a function yields a graph that's vertically stretched. But if you manipulate the inside of the function, that's horizontal, right? So on the next page, or on this page that we're on here, we can think of some examples. What is this doing? If f of t is 4 times the unit step function, u sub c.
Just increasing the magnitude of the step, I guess.
Yeah, this is just saying that it's going to behave like 0 as long as t is less than c. And it's going to behave like 4 when t is greater than or equal to c. Right? And so you might say this if you were reading the graph out loud. You would say it's off until t equals c when it turns on at a height of 4. Right? How about this one? What would this look like? If you had to write this as a stepwise function. Up until
same thing.
Up until t equals c, it's going to behave like 0 as long as t is less than c. And then after that, we just multiply it by -7. So we have a way to make a step up, but we also have a way to make a step down, if you want to think of it that way. Right? So you could think of it as off. That's really a height of 0. until t equals c when it drops down. To y equals -7 thereafter. So oftentimes we use the language of a switch, on and off. But on and off are really just user defined. If you want to call 0 on and then off is -7, you can call it that if you want. And of course, those of you who have played around with things like electricity have some sense of how this might be useful. Those of you who have done any kind of computer programming might have a sense of how this could be useful. A function that allows you to go from 0 to 1 is a function that allows you to create binary. A function that allows you to go from off to on is a function that models a switch, literally a switch in a circuit, right? Electric field is off, electric field is on. Right? So how about this? How can we write a function that behaves like a switch that starts off on? Starts off as in the on position with a value of 3 and then turns off, drops down to 0 at t equals 2. So how do we reverse this process?
I think you just reverse it piecewise, right?
Well, yeah, but how do we write it in terms of our unit step function? How do I write it in terms of u sub, looks like our switching moment is going to be at t equals 2. So this is really the value right here. This is saying c equals 2. That's the moment that we're looking for. But how do I make it so that it starts off at 3 and then it drops down to 0? Any suggestions? I'm going to start over here. I'm going to make this h of t. Well, if I just write u sub 2 of t, that's going to start off as 0 and then jump up to 1 when t equals 2. So what could I try?
Three minus 1u.
3 minus. Now here's the problem. If I just, it's okay, hit mute on your microphone there. 3 minus u sub 2 of t. If I do this, then it's going to start off as 0 for this. So it'd start off as 3 minus 0 up until the point that we have t equals 2, and then it would be 3 minus 1. So what do I have to do to modify this guy right here? I want this thing after t equals 2, I want it to be 0. So I want it to be 3 minus 3. So how do I make this second term? How do I make that unit function jump up to 3 and subtract 3 from 3?
3 minus 3 ut of t.
Lovely. And so let me manipulate it just a smidge so that you can see, in general, this right here, that second term, this is how we change the order. This is how we go from on to off. Do you see it? Because everywhere up to t equals 2, this is just going to be 1 minus 0. And then as soon as t equals 2, we get 1 minus 1, which is 0. How we feel about that? Does that make sense?
I think so.
Yeah. Time for a check-in. I just need to verify. Give me a thumbs up so I have an idea what's going on. Okay, we got some thumbs ups. Cool. So we have the ability to start with the switch being off and turn it on, and we can multiply it to any value we want, positive or negative. We also have the ability to start on and turn it off just by switching the order like this. So here's another challenge. I want a function that models a switch that's on with a value of 6.2 until t equals 14, when it turns off to a value of 3 after that. So I'm going to let you ponder this for a second. See if you can jot some ideas and see if we can come up with it. And then we're going to hop into Maple and see how to do this in Maple, how to communicate Heaviside functions with Maple. Anybody have a suggestion for something we can try? It's got to start off in the on position of 6.2.
Would it be 6.2 minus 3.2 times u sub 14 of t?
Well, let's see if this makes sense. How is this thing going to behave? It's going to behave like 6.2 because this thing is 0 initially. So it's going to be on 6.2. And then as soon as t reaches 14, we're going to be taking 6.2 minus 3.2. 6.2 minus 3.2, that's 3. Does that make sense? Does it work?
I think so.
I think so. Another way you could write this, get the exact same result, it's the more expanded version of this, is if you had 6.2 times 1 minus u sub 14 of t. So this is basically saying, I want you to behave like it's on 6.2 until t equals 14. And then you can add 3 u sub 14 of t. Do you see how that's really the same thing? Do you see how these two are really the same function? You could expand this out and you wind up with the exact same thing. Either way, this way when you write it out, you can actually see, oh, there's my starts off as off, or excuse me, starts off in the on position. That's the little code for it starts off in the on position. And then this guy right here is just an additional Heaviside function. So it works. Okay, so let's hop over to Maple and make sure that we know how to do this in Maple. So let me do a new share, get my Maple screen up. Okay, I'm gonna have to move my screen over because I'm operating on one screen, and so I'm trying to keep everything kind of off to the side. There we go. So now that we've played around with that, some space. So Maple understands the Heaviside function. If you just type in, it's capital H because it's somebody's name, capital H, which is odd because Laplace is not capitalized. Anyways, capital H for Heaviside, and then parentheses. And what we put inside the parentheses is, at first it seems a little strange, but it'll make sense. T minus 1. The Heaviside function t minus 1. This is code for u sub 1. Now notice it uses function notation. So if it's t minus 1, it's basically saying take the Heaviside function and shift it to the right 1 unit. Or the switch happens when t equals 1. So if I just hit enter, notice it doesn't do anything. It's just like, yeah, okay, Heaviside function. Gotcha. But if I do plot, and I say I want you to plot line number 5, Maple says, hey, I can do that. And look at what it gives us. It gives us 0, and then boop, it jumps up to 1. So let's check our last answer and make sure that it works. So I'm just going to type in, we're going to plot. Let's do I think it was Will. Was it Will or Jason who said that?
That was Jason.
It was Jason. Okay, so we'll do what Will just said, which is 6.2 minus 3.2 times the Heaviside function of subscript 14 means t minus 14. Now, of course, Maple's giving us this crazy graph from -10 to +10, so we have to change the t value settings. So I'm curious about 0 to, I don't know, 16. And sure enough, it starts off at 6.2 and then drops down to a height of 3. It's a little deceptive. The scale on this is 3. So it does exactly what we predict it to. It's 6.2 and then drops down to a height of 3. So the Heaviside function, the unit step function orientation, the way we write it like this, allows us to write in line without having to, have a piecewise function with multiple parts like that. But we can also do things like find the Laplace transform of the Heaviside function. So for example, the Laplace transform of the Heaviside function t minus, I'll just do t minus 1 just for giggles. And I want to do a Laplace transform on that. Maple says, no problem. It's e to the negative s over s. And that should look familiar. That's actually coming to us from this page right here. That one of the tables has our Heaviside function in it, right? And so now we can finally understand what the heck's going on with that first column, bottom row in the table. So it's a way that we can use Heaviside function with our Laplace transform. So Laplace plays nice with Heaviside functions. The next page in the notes, and we're not going to get very far on this. We're going to stop here in a second. But the next page in the notes, here, let me change my share here. Boop. So the next page in the notes deals with the question of, okay, but what about these switches is useful for us? Well, as I implied earlier, sometimes we want to be able to have a function like a sine or a cosine or a polynomial that's just off until a particular point in time, and then it switches on. And so we can make more complicated functions out of Heaviside functions, not by multiplying them by constants, but by multiplying them by variables, by multiplying them by other functions. And so here's an example on this page of a Heaviside function that's composed of a constant, a quadratic, and then another Heaviside function. And this is what it produces. It's off in the position of 2 until t equals 0, and then it drops down to 1, and then after that it behaves like t squared. And so making sense of this in terms of the Heaviside function as a, that's what I'm looking for, as a piecewise function, difficult. This right here is easier to manipulate algebraically. Even though you might look at it and not necessarily see how it plays out, because that is equivalent to a function that up until t equals 0, it's going to behave like 2, because this term is 0 and this term is 0. So it's going to behave like 2 everywhere that t is less than 0. And then as soon as t is greater than 0, or equal to, this thing is going to behave like 2 minus t squared minus 1. Or t squared and minus t squared plus 1. Right? Because you've got a constant here and a constant here. 2 minus 1. And then a negative t squared from that. So what we've done is we've created a function that behaves like a constant up until a certain point, and then all of a sudden it starts to behave like a polynomial. But we're able to write it in one line of code without having to worry about these piecewise brackets all over the place, right? It just requires us to manipulate the easier for the algebra. But this stuff over here, this is easier to visualize, at least for most people. So Heaviside functions can make algebra easier for us. It makes manipulation easier, but it doesn't necessarily make visualizing the graph any easier for us. So what we're going to do, or what I should say you're going to do, is continue on and learn how to use piecewise functions, learn how to manipulate piecewise functions, and then at the tail end of this section, we're going to learn how to involve these Heaviside functions into our Laplace transform method. Because any other method, integrating factor, the lucky guess method, none of those would work if we include a Heaviside function, because we don't have the chops to be able to do that any other way. Only the Laplace transform method works in those situations. So that gets us to the end here. Let me stop sharing. That gets us to the end for this morning. And then I'm going to finish up the 6.2 notes in videos, and I'll post those. And I will do those later today. I just have to get them done. It's going to be in the early afternoon. Early afternoon when I get them done. I got to get my voice back and have some breakfast and walk the dogs. And once I'm done with all those things, I'll put those videos up. So I'm going to hit stop on the recording here.